Hello, this is Roy Assaf from IBM Zurich. So I'm working as a researcher and also applying for the machine learning for diagnostics and prognostics of offshore wind turbine solutions in the ROMEO project. So this recording is for the second training pill, and I will go through the methods of machine learning for wind turbines. So this is the outline of the talk. I will start with an introduction, then I will go through the model development cycle when we're using machine learning, go over some pre-processing and modeling, and then move to the model selection criteria. At that, I'm going to focus on forecasting with a deep learning method, and then move and show some results for a test bench case study. So as an introduction, we know that wind turbine maintenance can be very costly, especially offshore wind turbines, because of the way the maintenance can occur. Maybe they will need to send helicopters, and it can be very costly at that point. And so there's a need to diagnose and prognose the wind turbine state prior to its failures. And to do that, we can use machine learning, which is very good at learning from data, these diagnostic and prognostic models. And that would be very good, an application with wind turbines, because wind turbines generate a lot of data. And this is because of all the monitoring systems that are installed on the wind turbines. So I will go into the model development cycle. So when we're using machine learning, there are usually three steps in the solution that we're developing. We start with pre-processing, and this is importing data, concatenating data, scaling the data, etc. Then we move to modeling, and this is where we define the model type or even the approach, if it's just general machine learning or deep learning, and there we define an architecture. Then we move to post-processing, and this is basically where we are comparing model results with the input, we are smoothing forecasts, we are formatting results to the way it's expected to be in a database. And then based on the feedback, we can reiterate on any of these steps until we reach the performance required. The pre-processing, I'll go over a couple of important pre-processing steps when we're working with time series data, which is the main data type that we work with when we're working with these offshore wind turbines. And here, it's very important that we handle the raw data format, right? So the raw data format doesn't come in a structured manner. We would need to append that to something like a Parquet format, which is a more compressed format, and that's more suitable for storing in a database. We do some data cleaning, and this is where we remove duplicate entries and remove NaN entries. And basically, we also generate data quality reports, and we very importantly scale the data for machine learning. So the scaling can be applied using min-max scaling or z-score normalization, and this is basically where you take the data and you normalize it on the zero axis. And very importantly, when we're working with time series, we want to generate these samples for the machine learning ingestion. And as you can see on the figure on the right, this is how you can generate those samples. We can basically use a sliding window over the time series and slide that, generating samples that can be fed into the machine learning. This is very important because machine learning algorithms expect a particular size of data. So we cannot infuse a size that's bigger or smaller at different times. And therefore, generating samples in this manner is the optimal way when we're working with time series. Another very important part of pre-processing is to drop low entropy features. And low entropy features are basically when we have a count of a particular value that's relatively concentrated in few values. These features are not really useful in machine learning. In fact, they can be very noisy. And so it's very important that we drop these kind of features. Another important step is to impute missing data. So when we have missing data in the time series, we would like to fill those gaps with some by using linear interpolation or some more complex approach. Otherwise, we would drop these missing data if they are in a very large concatenation. So now I'll move to the model selection criteria. So again, after pre-processing, we will move to modeling, and I will explain a bit on how to choose the particular type of approach with machine learning. So we start with the first question, which is, do we have labels? If labels are available, then we can ask another question, which would be, is there class balance? So do we have balance between the different classes, maybe failure and non-failure in this case? If yes, then we can use supervised learning. So this is the most well-established branch of machine learning. And this is something where we can apply things like classification. But if we do not have class balance, then we need to ask another question, which is the minority much smaller than the majority? And in other terms, in the terms of wind turbines, we can think about it in this way. Do we have a lot more healthy data than we have failure data? If so, then we cannot apply these kind of classification approaches. And we'll have to go to anomaly detection and clustering. Otherwise, if they are not very far apart, we can do something called minority oversampling, where we can rebalance these classes and then go back to classification. And then if we go back to the top of this tree, we can see that if we start with no labels, we can again look for something called the target variable. So this is something that we're trying to predict. If we do have something like that, then we can maybe forecast that value. And this is the case that we're going to be presenting later in this presentation. If not, we can move to unsupervised learning, and then we can choose between clustering and anomaly detection. So here, as I mentioned, I'm going to focus on the forecasting. And what you see here is called temporal convolutional network. This is what's shown on the bottom figures. And the approach we're doing is multi-step ahead forecasting. So we're first forecasting multiple steps ahead of the time point that we are at. And what we are trying to predict is something called the health index. At this point, we are working with vibration data, or what I'm going to present is vibration data. And so this is related to the root mean square of the frequencies of interest. I'll go a bit more detail into how this TCN works and why it's very important. So again, this is a deep learning method. So this is more on the state-of-the-art approaches that we've got. Usually people think about recurrent neural networks as the go-to method when we go to deep learning for time series. However, TCN has proven to be better in performance and faster in the recent years. And so this particular type of network is called the TCN. Again, it's a temporal convolutional network. It employs these dilated convolutions, which increase the receptive field. Basically, you can look at more of the data all at once. It has causal convolutions, which is very important because there's no information leakage from past to future or future to past. And so this is very important that we do this kind of approach. So we have, if we had to run in real time, that would work correctly. Also, this is better in performance than LSTM and GRUs. So these are RNN-based architectures. And this is because it can process even longer sequences. Again, this goes back to these dilated convolutions that it uses. Also, RNN-based architectures use a lot of memory, while TCN uses a lot less. And finally, TCNs also can be used in parallel. So this is because you are applying the same filter in each layer. So this can be done parallel and go a lot faster. And and as I mentioned before, we can have a long input sequence, and this is very important for these kinds of problems where you're considering maybe month at a time. And you cannot do that with traditional machine learning, and RNNs will suffer while dealing with that. So here, this is a case study that we've got in ROMEO. This comes from a test bench. So this is data from a test bench where we are collecting really vibration data using vibration sensors. And so what you see here in the first figure on the top left is the 9 harmonics of the failure frequency that are highlighted. So we start by basically plotting this FFT bands, and then we highlight the frequencies of interest that we want to work with. What you can see here on the right, also on the figure on the right, is a zoomed in version of what you're seeing on the left. And basically, when we concatenate all of those in a time series manner, what you will get is the figure on the bottom. And here we are showing all these harmonics and their evolution in time. And so the higher the magnitude or the Y value that you are seeing here, the more displacement is occurring in the wind turbine. And so therefore, we are moving towards a failure in the wind turbine. And we would like to predict that beforehand, because once we predict that, we can take some preventive action and lower the cost of maintenance. And then employing the TCN, what I can show here is in the figure on the bottom right. So here we're employing TCN to do this RMS forecast. So again, we're forecasting these harmonics, the values of these harmonics 16 steps ahead of time. And the result can be seen at the bottom right. Here, which shows the first harmonic, and which can be seen in blue. So this is the original data, and in orange, you can see the predicted data. Again, this is occurring 16 steps ahead of time. So we don't know what's going to happen, and then we predict what's going to happen in the 16 next steps, which is equivalent in this case to 16 days almost. And this depends because of the way the data is sampled. And this is another example, again, coming from a test bench. This is, as you can see, a little bit more complex in pattern, but again, we can see that TCN can deal with it very well. Once again, these are qualitative results, just to show how TCNs can perform well on such problems. And again, once we have these predictions and we can say maybe the remaining useful lifetime of a wind turbine, we can plan actions accordingly, and then based on those, we can lower the cost of maintenance, which was en gros the whole concept of the ROMEO project. Right. And yeah, thank you for listening. And if you have any questions or you want to look up any more information on the ROMEO project, this is the website, so www.romeoproject.eu.